could be part of the improvement. In fact, we are slightly better. It sits about 54, 55. So if you keep yourselves to 54, 55, and with the weather improving, I'm sure that will happen anyway, then that might be okay for Mondays. I have posted the homework, but you can't access it because this is a university where if you don't know what you're doing, you can't get anywhere. So I can't figure out yet how to open it up for you guys to access it, but I will do that by the end of the day. But it's there, I have double checked. And I will cover this, the homework briefly, the contents of the homework today. It is due next Monday at 5 p.m. Hard copy or electronic copy, it must be either emailed to me or you bring it to my office. No delays. Now, as I mentioned, throughout the course you will be needing some form of software that will do the classical laminated plate theory. And one that is readily available to anybody in our aerospace engineering building is called Colibri. If you get on any of the computers in that building and you access Colibri, then you can use it. In addition, which goes with the book, there is a app for those who have iPhones or iPads, and because it's complicated to switch back and forth, I will not do the demo, but anybody interested during the break, you can come and I'll show you, or you can see how the app works, which does pretty much the same things. And we're now continuing. Today we'll also do engineering by compromise and voting engineering. You'll see if we can design something by voting and democracy, whether democracy is a way of designing structures, which we'll do in a little bit. We were talking about, we finished the classical laminated plate theory in terms of being able to calculate for a given laminate the stiffnesses. And I use the plural because we have the membrane in-plane stiffnesses and the bending out-of-plane stiffnesses and coupling. And then based on those and applied loads, you can calculate strains and curvatures. And then we talked a lot about, failure criteria, which is the next step. You use all these strains and stresses to try to predict failure, because ultimately you want to design these structures for lower weight or for a bunch of other attributes that we will be covering today briefly. And in general, today's lecture is finishing up on some things we started talking about in the design process, as they are more specific to composites, but they are general enough that would be good to have in mind. And some of these aspects you will see in the homeworks and the final projects as we go through the course. Then we'll talk a lot throughout the course, briefly starting today, the fact that a structure can fail in more than one failure modes. In the standard metal structures, you know, you can have buckling or yielding, and you don't know in advance which is going to happen first. So in composites, it gets much worse. There's many more, and you can anticipate that by thinking of about the fact that you have fibers and matrix, and either of them can fail, or the interface between them can fail, and then in sequence can trigger different types of failure modes, and that, as a result, would make it more complicated, more challenging, and more interesting. And let me say up front that it becomes crucial to know the failure mode for which you are analyzing. If you don't know it, then you might miss it. This finite element code or whatever you are using is tailored to the construction that you made up, and it may not be able to tell you it's going to fail at this specific failure mode, and it might miss it. I'll show you examples throughout the course. Then we'll do the full-blown 17 equations in 17 unknowns for anisotropic elasticity, and we'll try to even start solving those for some relatively simple cases where we can solve them in closed form. So, having said all this as a background, we were saying that minimum weight is a big deal, but as a weight goes, you cannot simply minimize the weight if you pay no attention to the cost. And you've seen all kinds of comparisons between how much money one is willing to pay for every kilogram of weight saved, whether it's a space structure, which is much higher than an automobile, which is much lower. In fact, the numbers, just for now that I'm thinking about it, if you're doing your regular family car, then it's less than 2 euros per kilogram of weight saved that the manufacturer is willing to pay, because that translates to certain fuel savings and so on. If you're doing a higher performance car, but not Formula One yet, so it would be between the electrical cars and higher performance top of the line, then it's less than 6 euros per kilogram. Formula One approaches 20 to 50. Okay, so this is regular. This is higher performance. This is Formula One. Well, actually, depending on whether you are from Southern Europe, where money is no object, then it's more like 150 euros per kilogram. Now, if you have a regular civilian transport airplane, it's anywhere between 350 to 2,000 euros per kilogram, and the big difference here is based mostly on the anticipation of what the fuel prices will be in future years. That is, an airline today, or a manufacturer of an airplane today, has a certain impression of what the life cycle costs will be for that aircraft. And those are extremely strongly dependent on the fuel prices. And so there are today's fuel prices and what we think they will be in the future. And depending on where we think they'll go, then you can get numbers that can be in a quite wide range. And then, of course, space, the final frontier. Okay, so this one is civil transport. And I can give you military. Starts at 1,000 and goes to, I've lived through a program which it was 15,000. This actually is an interesting story related to this. And then space is from 10,000 to 50,000 maybe, depending on, again, the specific application. Now, this is what usually happens is you have a program, you go through the design program, you start building, or you finalize the design and you realize most of the time that you're overweight for 10,000 reasons. The loads go up, the mission changes, your optimistic original estimates were wrong, and so on. So then the customer will penalize you, especially if it's military. Every kilogram you're overweight, the original weight, whether it's gross weight or weight empty. Then you have these huge efforts throughout the company designing, throughout the factory, to come up with lower weights. So, and they give incentives to the engineers, and they say for every, basically we pay you the amount that the customer is willing to pay. So I was in a program which was at 15,000 euros per kilogram of weight saved. So some of the stress engineers had been smart enough to have a little bit of a safety, extra safety factors in their designs, a slightly higher thickness, because the loads go up, because of whatever, anticipating and not wanting to have to the last minute to go and change everything. So it wasn't highly optimized, but it was optimized. So when they said, I'm giving you 15,000 euros per kilogram, these guys, showed up, and they were saving kilograms left and right, and they were making lots of money, because this was real money paid to their pockets. So on the one hand, if you are inefficient in your design, then people will tell you, you are not good enough, we don't want these kind of people because we're trying to save weight. On the other, if you are smartly inefficient in your design, you can make a lot of money. So cost is a big deal, therefore, and it can range, again, as I was saying last time, from the recurring, which is every time you make it, how much it costs you, labor hours, wear and tear of equipment. Non-recurring, which is the equipment, tooling, molds, and so on. Assembly cost, it's a very big deal, about 30% in a composite structure, about 30 to 45% of the recurring cost is assembly. So if you can minimize assembly, and by assembly we mean putting parts together, and that means minimizing the number of rivets, minimizing the number of parts or maximizing their size, so co-curing a lot of parts, that can really make a big difference. Low maintenance, the airlines are extremely interested in that, especially if you have composite airplanes where you have to retrain all your personnel to know how to do repairs, how to do inspection, and how to evaluate what they are doing. They have been working with metals for decades, and now it's composites. Replaceability across assemblies, I mentioned it last time, to be able to take apart from one aircraft and put it on another aircraft of the exact same model. It's not as easy as it sounds if it's not designed correctly. Natural frequency placement, zero coefficient of thermal expansion, and so on. Okay, that's what you try